Welcome to The Explainer. Today we're unpacking a highly complex and honestly often completely hidden cost embedded right in the middle of our renewable energy transition: water. When we hear biofuels, we instantly think green energy, lowering carbon footprints and ditching fossil fuels. But behind all that green promise, there's a massive reliance on a very finite resource. Let's dive right into the source material and see what it reveals about the true water intensity of biofuels manufacturing.
Right out of the gate, we're hit with a striking paradox outlined in the standard. Yes, biofuels are absolutely crucial for replacing traditional fossil fuels, but the actual process of refining them, it is highly water intensive. Now, the documents do note that this water use might be relatively modest compared to what it takes to actually grow the agricultural crops for the fuel in the first place, but the refining consumption is hyper-concentrated. You've got a refinery sitting in one specific location pulling massive amounts of water, which can severely disrupt local ecosystems, spike regulatory risks, and trigger some intense tensions with local communities.
Let's break this down. Section 1, the thirsty biofuel refinery.
To really grasp the scale of this, imagine zooming right into the pipes of a facility, like watching a rapid time-lapse of its operations. You'd see massive volumes of water constantly flowing through four vital manufacturing stages. First up, feedstock processing to prepare the raw organic materials. Then, fermentation, converting those sugars. Next is distillation to separate and purify the fuel. And finally, you have these massive cooling towers working completely overtime. Literally every single one of these steps is incredibly thirsty. If there's a disruption to the water supply, the whole shebang grinds to a halt.
What I found super fascinating in the source material is how strictly it defines water consumption. It's not just a casual loan from a nearby river that gets put right back. The standard specifies that consumed water is water that completely evaporates during the process, water that actually becomes physically incorporated into the finished biofuel itself, or water that's discharged into the sea or a totally different catchment area, basically meaning it never returns to its original local source. That water is gone from that community's ecosystem for good. And the water that does leave the facility as effluents, well, it is far from pristine. The refining process leaves behind wastewater loaded with contaminants. The standard specifically flags salts, various organic compounds, dissolved solids, and phosphorus. So refineries can't just dump this water back out. It requires heavy, expensive treatment to avoid wrecking local habitats.
Moving on to Section 2, Mapping Global Water Stress.
Now that we've seen how thirsty a single plant is, let's zoom out to a macro, global view. The standard requires biofuel entities to map out their entire global operations to measure geographic risk. And they can't just guess here. They're required to use sophisticated, standardized data tools, like the World Resources Institute's Aqueduct Water Risk Atlas. This lets companies and investors pinpoint exactly which facilities are sitting in highly vulnerable, drought-prone regions. Here's the kicker. Refineries must disclose exactly what percentage of their total water withdrawn and their total water consumed falls into two specific red zones. We're talking high baseline water stress, where 40 to 80% of available water is already spoken for, and extremely high baseline water stress, which is anything over 80%. If a biofuel company is pulling the bulk of its water from these regions, their business model is incredibly exposed to water scarcity, and for sure, investors need to know about it. Which brings us to Section 3, the ripple effect of risks.
Extracting heavy concentrations of water from stress sources sets off a massive ripple effect across a business. The standard actually divides these constraints pretty starkly. On one side, you've got physical, environmental threats, droughts, seasonal variability, climate change impacts, and aquatic impingement, which is when local fish get trapped in the water intake systems. But clashing directly with that, on the financial side, are volatile water prices, direct competition with local municipal users for drinking water, and huge community pushback. A biorefinery simply cannot survive if the town it operates in runs dry.
Actually, the risks don't even stop at the intake pipe. Pumping treated water back into the environment carries its own severe risks. One really specific detail the standard highlights is the sheer struggle of water temperature control. Discharging water that is way too hot can absolutely devastate a local river ecosystem. Failing to navigate these strict discharge permits leads to liability, reputational damage, and intense scrutiny from NGOs and regulators.
Let's look at solutions. Section 4, Mitigating the Water Trade-offs.
Facing all these operational and reputational threats, how do biorefineries actually fix the problem? Entities have to transparently disclose their specific short-term and long-term mechanisms for hitting water efficiency targets. Are they setting absolute targets to just cap their usage, or intensity-based targets, trying to use less water per gallon produced? They have to lay out exactly what they are doing. The actionable mitigation strategies investors want to see usually involve heavy investments in efficiency. We're talking advanced water recycling systems or even closed-loop systems where the exact same water cycles through the plant over and over again. It also means process innovations, like redesigning intake pipes to reduce that aquatic impingement and protect local aquatic life.
But, and this is a tricky balancing act the standard acknowledges, companies must disclose if these water-saving practices accidentally trigger what's called a life cycle trade-off. For instance, running a state-of-the-art closed-loop recycling system takes a massive amount of electricity. If that power comes from fossil fuels, the refinery might save local water, but inadvertently cause a huge spike in their greenhouse gas emissions. They literally have to explain why they chose that specific trade-off.
Finally, Section 5, Tracking Compliance and Enforcement. So what happens when that balancing act fails and a biorefinery runs afoul of local water regulations? The standard strictly mandates that companies must report all incidents of non-compliance associated with water quality permits. Total transparency is the name of the game here. Investors absolutely have a right to know if a company's water management is triggering legal breaches that could hit the bottom line.
Any formal enforcement action has to be laid bare, whether it's an administrative penalty for a hazardous discharge, a judicial action, or exceeding total maximum daily load limits, which is basically the maximum pollutant a water body can take and still meet quality standards. If a refinery crosses that line and gets hit with an enforcement action, they absolutely must disclose it. And get this, the reporting requirement is absolute. There are 0 exceptions based on measurement frequency. It doesn't matter if the discharge is continuous, like a daily average flow, or non-continuous, like a sudden localized release. If a violation happened that resulted in formal enforcement, it goes on the record, no exceptions.
Which leaves us with a pretty provocative final thought for today's explainer. As the world rapidly scales up biofuel production to combat climate change, we have to look at the whole picture. Are we inadvertently trading a global greenhouse gas emissions crisis for localized community water crises? The standards are there to track it, but it's really up to us to pay attention to the trade-offs. Thanks for joining me to unpack the mechanics of water and biofuel manufacturing today. Keep asking those big questions, and I'll catch you next time.